I've been rejected. No, but they've been rejected. Is there anything in particular? Yeah, that's a good point. That might be right.
Because otherwise it's
Yeah, I know. I agree. Oh, he won't be. Like a funky dog.
Welcome everyone. Welcome to our penultimate talk with Selfportraits there. And it's my pleasure to introduce to you Professor Alain Goriely, who has come over from Oxford, where he's the director of the Oxford Centre of Industrial and Applied Mathematics and director of the International Brain and Mechanics Lab. Please welcome Professor Goriely for his talk about dimension mathematics.
Thank you, Philip, and I wanted to thank Cambridge University Scientific Society for the invitation. It's a great honor to be here tonight. When I was asked to give a talk, my first reaction was, well, yeah, it sounds like a cool idea, but I also thought about that idiom in English, which is to bring back the coal to Newcastle. I don't know if you're familiar with that. Newcastle being an industrial coal mining town, bringing the coal back is an act of repetition or useless, if you want. I'm saying that because, as you see, a big part of this research, or the main point, of some of the main discovery have been done by people here in Cambridge. Actually, within this department, there is a very active group, and one of the top group in the world. And in psychiatry, there are also groups looking at other aspects of the brain that I will also consider and tell you about. My perspective is probably a little bit different, being a little bit more mathematical, trying to merge some ideas at different scales. The work I'm presenting today is collaboration with essentially these two groups, Ellen Kuhn in Stanford in mechanical engineering and Matthias Jucker in Tübingen, who has the largest research group in Alzheimer's disease in Germany. So I started with this nice piece of art from Greg Dunn and Brian Edwards in the US, just to give you a little bit about the lay of the land here. We're going to talk about the brain, and I just wanted to look at some of the main important parts. So this is a sagittal cut, so it's a sagittal slice, cut your brain through the nose. And what you see is the front is the frontal cortex. So this is where a lot of what makes us take place, a lot of feeling, empathy, understanding of each other, socialization. The top here, with its very large neuron going down, it's the parietal lobe with the motor neuron going down the brain stem. In the back, you'll have the occipital lobe, so a lot of huge part of the brain dedicated to vision. And the cerebellum, the little brain in the back here, we're not going to talk about it, but it's much more related to basic process such as breathing and proprioception and so on. So the other structure you see from the brain is that what you see is this long filament. You see this long filament going from the top, the cortex. Cortex is this small part of the brain, a few millimeters, that contains much more of the cell bodies. And the cell bodies are connected to other parts of the brain to these long processes called axons. This part of the neurons. Axons extremely long with respect to the cell size. In the middle, you have the basal ganglia, who acts a lot related to many processes related to motor control, but also act as a relay mechanism for different parts of the brain. It takes information and redistributes to other parts of the brain. One of the great advantage, or one of the great progress of the human brain, is its ability to connect to different parts of the brain in a very efficient way. And the message of the talk today is that the same ability, the same advantage that we have in this powerful connection makes us also prone to some of the neurodegenerative disease related to dementia. So let me start for real. Chapter 1, Ik heb mich verloren. So this is what August Detter says when describing her own condition. August Detter, for her story, is really patient zero. In 1890, she started having troubling signs. She was in her 40s, what we would call today early onset dementia. She would have problems with memory, day-to-day memory. She couldn't sleep. She would wake up in the middle of the night screaming and dragging shit through the house. She would have part vegetative states for a long period. And eventually, soon enough, she was admitted to the Herrenschloss, so the castle of the insane. And she was followed for many years, and we have a very good record of her condition. In part, when she was asked to describe herself, what happened to her, She says that she's losing herself, her own sense of self. And one of the doctors who followed her was Alois Alzheimer. And in describing her illness, he called it the disease of forgetfulness, what we would call today Alzheimer disease. Eventually, August died in April 1906. And Alzheimer wasn't there at the time, but he asked for part of her brain to be shipped to her, to be sent to her in Munich. And using the best imaging techniques of the time, which new staining techniques, what Alzheimer identified within the brain are two typical hallmarks of Alzheimer's disease, and it's still the standard of how we describe it. And these are aggregate, very large aggregate of certain type of protein. The first one we know now is amyloid beta. It's an extracellular protein that makes this plaque amyloidosis that you find in patients with Alzheimer's disease. And another type of protein aggregate called neurofibrillary tangles are made of these very small protein, tau protein, that are intracellular protein that are essential for the stabilization of axon. They cross-bind a microtubule within the axon. And certain type of this protein can form large aggregate that's formed in this brain. And so the description at the time was that the disease is associated with that, which is still what we believe. We know for sure that the disease is associated with the two protein. The causal mechanism are not completely understood, and there is a lot of controversy, but it's incontrovertible that proteins, these two proteins and this protein aggregate play a role in the disease. Now, to give you a little bit more of the human dimension of the disease and what it does, here is another very interesting case, the case of William Butler Mullen. He was an American painter born in Philadelphia in 1933. He moved to Oxford to go to the Ruskin School of Art in the 50s, in 57. And in the 90s, and that's some of his art, he became quite a good painter with very strong sense of color, pop imagery, and all that, so quite famous. But in the 90s, he started showing troubling signs. He couldn't remember day-to-day events. He couldn't do his necktie properly. He couldn't do his house finances. So he went to see his GP, and GP thought maybe it was dementia, maybe it was depression, gave him a series of tests, MRI, and so on, and he was diagnosed in the 90s, so it was in the 60s. He was diagnosed with Alzheimer's disease, or probable Alzheimer's disease. There was no categorical diagnosis at the time. The diagnosis would come after that, final diagnosis. So, but with his wife, who was an art critic, he decided to keep a record of the progression of the disease through his art, and decided to do a series of self-portraits as it evolved. So here is the 96, you see, still very much in control of his art, it's reflection. And I find that fascinating because these self-portraits are really somewhat the ultimate view of the artist into himself. Here is 97, you start seeing the difference. But then by 98, you see a very fast progression of the disease, 98, 99, and 2000. You see, it's still, I still enjoy very much the art at the end, but it's really not in control of the perception, the three-dimensional perception, is not anymore in control of the fine motor control that he needs to paint or to draw. And he's losing, through his image, he's losing himself, as you can say. Now, it's very interesting because you can use this as a marker to stage the disease. And the disease has been staged, the progression of the disease can be staged through analysis of slice pathology, so histological analysis of brain slice taken after the death of an individual at different stages of the disease. And this is the work of the Brack and Brack, husband and wife, who looked for many years into hundreds of cases and tried to establish the progression of the disease. And what they could say is that the disease is has different stages corresponding to different protein invasion. In this case, it's the tau protein that you see in black for the staining. So that part here. So here in the bottom, the hippocampus, so the place where memories are stored. So it's always the first part of the disease. So different stage that you can see on histological slide, but also associated with cognitive trouble. And Alzheimer's disease and a lot of these neurodegenerative diseases are very homogeneous in the presentation. They systematically invade the same part and mostly have the same series of symptoms, starting with amnestic syndromes in the first part of the disease. So both the episodic amnesia, so day-to-day event, but also semantic, losing the notion of an object. You don't recognize. If you see a cow, it's not like you don't remember the name, but you don't remember the meaning of the object, or that it's an animal or something like that. Then moving on to cognitive problems, that's problems with abstraction, problem solving, judgment problems, so doing finance, I guess, and things like that. And then moving on to instrumental problem in the next stage. An instrumental problem, aphasia, inability to recognize or properly do speech, agnosia, inability to recognize object, apraxia, inability to have fine motor control, even though there is no problem directly with your nerve or muscles, and so on. And the last part of the disease, when all the cortical area are infected, then you have large psychobehavioral trouble, large period of apathy, violent outbursts, and so on. So very serious problem. So this is a coronal slice where you see the evolution, but you can also map the evolution as a sagittal slice, and it starts in this region close to the brain stem, typically for the tau protein, go to the entorhinal cortex, start invading the frontal part of the brain, so the prefrontal cortex, and then going around and invading eventually all parts of the brain. All these effects. Most of the dementia, if they're allowed to go all the way to the end, have this global invasion of all the parts of cortical area. So it's interesting to look at not only Alzheimer, but to look at it in more globally into classes of neurodegenerative disease. So Parkinson disease is associated with another type of protein, alpha-synuclein, which plays a similar role that the tau protein as intracellular. And here again, it starts in the brainstem and invade basal ganglia and so on, and has these invasion patterns that are also very typical and that have also been mapped through the disease. Here is another one, ALS, amyotrophic lateral sclerosis. Here it starts at the parietal lobe and directly affects your motor control, and then goes straight down in the brain stem, and then you have these invasion patterns that go into the frontal cortex. Again, this is not a protein. It's not an axonal protein, it's a cellular protein. It's present in the cytoplasm mostly. It's called DTP43, and it's characteristic of the disease. You see there is something very strange, and I'll go back to that with ALS, is that whereas in the late stage you have a lot of involvement of frontotemporal degeneration, very typical of ALS patient at the end, there is very little or no involvement or no invasion of the disease in the back part of the brain, in the occipital lobe. And why it is the case is not quite clear, so I can't go back to that. So this is the invasion patterns in terms of the biochemistry that you see. But it has also another effect. As the disease invades its different part of the brain, it also kills the cell, and the cells are systematically removed and the brain shrinks. Normal brain also shrinks. This is the typical pattern of brain shrinking. So in red you have women and in blue you have men. So this is a data set that I got from a paper in 1978. The last time that was done, we looked at, I think, 10,000 autopsy reports and look at the weight of the brain in each case and the reason of death and so on. And what you see is that in early years, so from 0 to 20, in this region here, you have a very large growth of the brain, going all the way to an average of 1300 or 1400 something, depending from men or women. Right? So if you might still be in that period of your brain growing. And then you're mostly in a steady period here, nothing much happened. And then in later in age, you have a shrinking of the brain that can be 11 to 12%, 11 to 15%. But that shrinking is mostly not neuronal cell, not the cell that we need for most cognitive process. A lot of it is related to other cells or extracellular space, the glial cell and so on. There is only 2 or 3% loss of neuronal cell actually. So that this is normal aging. Maybe people are slower, but they have all their heads. It's perfectly normal, and you can go a long time like that with having normal aging with no sign of what people call senile dementia. People start acting up because they're old. No, there's no reason for that in normal aging. Here is the difference between normal brain at death and Alzheimer at the same age, around 65. And right away you see the difference between what was a healthy brain before death, nice round in good shape, and the Alzheimer brain that looks more like a walnut, a shred walnut. And if you put them next to each other, you'll see right away that the difference between the two, and the typical sign that you will see in autopsy, you'll have this enlarged ventricle, so the ventricle is where the CSF is generated and it's turned over, the cerebrospinal fluid that bathes the brain. You have an opening of the sulci, so the sulci is this valley that you can see on this side. They're all closed here on that side, but they open there. You have a thinning of the cortex, which is very significant because cortex is where most of the higher cognitive processes take place, and a shrinking of the hippocampi also, again related to memory. So this is on the physical side. So one of the main questions for people dealing with Alzheimer is there certain quantities that we can measure that will tell us where you are in the disease, or the disease evolves. These are called biomarker abnormality in clinical studies. And there are few for Alzheimer's disease. You can measure in the CSF the presence or the absence of amyloid beta, the plaque. Since the plaque is forming within the brain, there is not as much in the cerebrospinal fluid, so you have a decay of that. You can look at the tau protein, or they are also in the CSF. You can look at the MRI, just the shrinking of the brain. You can look at PET, so that more directly related either to targeting the protein or looking at the metabolism, so the metabolic environment of the brain. Or you can do cognitive tests. And this, if you look at any review in the last 10 years, you'll have a reference to this paper. These are called Wheeljacks Curve from Dr. Jack. And it's drawn, it shows you that first you would see amyloid beta, right? That's the level of detection, so it's the first thing you would detect. And then you would see CSF, then you might measure atrophy, and maybe you'll see more of the sign of dementia, the cognitive sign. All this would happen before sign are actually present, cognitive sign are present. I thought that was great. The problem is solved. Mr. Jack has this curve, it must come somewhere. So you go back in the paper, you read, it says, what are these curves? For a mathematician, this curve must come from somewhere, typically from a model or something like that, or maybe from data. But actually, you find out that Mr. Jack has actually drawn the curves on a piece of paper and put them in the paper. There's nothing wrong with that. It's a way to express an idea, and the idea is that Mr. Jack says, Dr. Jack says, the disease, this biomarker starts slow and then grow quickly and then saturate. And I'm representing that on a graph. It's a way for me to formulate this idea visually. Because the only type of data you can find looks like that. So if you fit data, if you ever try to fit data, you say, okay, I don't know about you, but it doesn't look like the one on the left, right? So maybe the best you could do is fit a straight line to that. Maybe a line like that, right, for some of them, or maybe another one like that. But for me, it is a very different behavior in terms of the evolution of the disease, and I'd like to see where they're coming from and how you can explain it. So now we have a few questions in terms of understanding the progression of the disease and challenges ahead of us. I'm very much interested in the dynamics of the disease at the global level, the spatial temporal evolution of the disease. So I want to understand the staging, and I want to understand in a way that's not necessarily disease specific. He said, if these diseases have the same characteristic with different protein, would they follow somehow the same type of universal or generic progression? But I also want to relate it very much to the physical aspect, to the atrophy. Can I go from the spatial evolution of the disease due to this protein to the actual atrophy? And why I want to do that, because now we have so much MRI imaging data that I want to be able to correlate and validate model against MRI data for atrophy. But mostly I want to understand how that happens. And then I want to see if I can get biomarkers. Eventually, the next step, which I'm not going to talk about today, is I want to understand if I know the evolution of the disease, can I say something about the cognitive decline that goes with it? And that's related chemical and physical model to neuroscience model for the behavior of the brain. That's something else we're working on now. So, chapter 2, un peu d'analyse et de calcul. So the question is, the natural question, whenever I give a talk on this subject, is why would you want to do mathematics? This is obviously an extremely complicated disease. $30 billion have been spent, no cure, no treatment available, essentially. I just look online, about 300,000 science papers have been published on that topic. Why mathematics would do anything for the field, right? So, to answer that question, I can only turn to Daniel Bernoulli in 1760, who went to the Academy of Science in Paris and said the following thing: I simply wish that in a matter which so closely concerns the well-being of the human race, no decision shall be made without all the knowledge which a little analysis and calculation can provide. And what he was referring to was he was doing the first probability model for the evolution of smallpox in France. And he shows that with proper mass vaccination, you could save between 25 and 40,000 people. Just a little bit of analysis and computation. And so on the subject of dementia and mathematics of dementia, about 100 papers have been published on the topics. So maybe, now that everything else has failed, it's time to go back and do a little bit of analysis and computation, as I'm about to do. But to do that, to base that, I'm not going to start with the flavor of the day, so I'm going to look at the data, and the data is going to tell me everything. There's too much data. What you really need for this type of topic is go at the heart of the mechanism, and go back to possible mechanisms that you can test to mathematical modeling. An interesting mechanism that's been proposed by a group here in Cambridge, and Walker in UK, Walker in the US and Walker in Germany, is called the Primelike Hypothesis. And the idea is that these proteins are very much like prion proteins in prion disease. There's some form that you can start with a healthy toe, which is normal in the normal homeostasis regulation of the axon. So let's think of a toe protein, and this toe protein can misfold and turn into a toxic protein. Somehow the protein might take a different shape. And it's toxic in the following sense, is that it can, whenever it meets a healthy protein, it can turn that healthy protein into a toxic protein and aggregate. It sticks to it and changes it. A little bit like in a zombie movie. You have one zombie one day, and then it finds a healthy person, and then you have two zombies, and then you have a group of zombies, and then the zombies grow in group, and sometimes they go in little groups, they fragment, and then they form larger and larger groups, and they invade the streets, and soon enough they form entire crowd, which in the case of the tau protein are now neurofibrillary tangles, and that was eventually would kill the axons, and that, you know, the end of the movie, what happens there. There is no way to stop that process once it's gone, really, past a certain size. So what is the model that you can draw out of that? From this process that is described in the literature that's been tested at the chemical level, we know what it takes place, we know the kinetic rates and so on. What you can do is follow the concentration of the good, the healthy, and the toxic protein in space and time. You define that as your main variable. And then you write, based on the known chemistry, possible rate equation for both aggregation and fragmentation. And then that's at the local level, so they can interact with the environment, but these can also be transported. An important aspect of the transport process is these, for instance, are intracellular protein, and they can be transported very quickly along the axon in the brain, this long filament that we saw in the first slide. And then the idea is that past a certain level of concentration, damage happens, and then atrophy takes place. And this is what happens, as you saw in the top there. Let me go back. So here, so this is an axon here, and the axon being invaded by tau protein eventually pearl and disintegrate and is removed from the brain. So how do we build a model out of that, a mathematical model? The minimal model would have only two populations, the good guys and the bad guys, the healthy and the toxic protein. So in this case, you start with the blue and the red again, and they form an heterodimer, blue and red, but the red is going to transform the blue into a red, and then you have two reds, and they can separate into two. So there is a lot of steps, and the kinetic can be quite complicated, but you can also say, forget about the complication, that's the luxury of doing mathematical model. I want to just go from the first state to the last state. So I have a very simple process. It's now P plus P tilde, good plus bad gives two bad guys, right? So if you can translate this chemical equation into mathematical equation, differential equation, if I think as P as a function both of the position and the time, I can write rate equation, and transport equation that contains a production term, that's the normal production of tau protein that's done within the cell. There's continuous clearance of this protein by various processes. So in normal homeostasis, you have production and clearance that always takes place. It's removed. And when clearance doesn't work as well, then that's when you start accumulating this unhealthy protein. And then you have 1/3 from the conversion that can take place. You take from one population and you give to the other one. So that minus K12 plus K12. Then there is the transport part that is a little bit more tricky. If you had just isotropic transport, that would just be normal diffusion, like the heat equation, evolution of concentration. But in the brain, what you have is very fast transport along the axon and slow transport away from the axon. So you can do experiment, very nice experiment, where you seed with the blue the tau protein, and they go very quickly along the axon, but to exo and endocytosis, they can also diffuse in the intracellular space and infect other axons. So what you want is fast axonal transport along this direction and slow axonal transport perpendicular to them. So you can write that as a tensor, a diffusion tensor, that has one preferred direction and one slow one. The form is not important. This is really the last complicated equation for today. What is really important is the meaning that's attached to that, and that this equation is rather simple, but just encompass fundamental process that take place. So just to understand what this equation, how they behave, you can look in one dimension. So just along one dimension along the axon, and just look at the evolution of the toxic protein if you just run the equation. So I start here with a tiny little bit of toxic protein, and I just let it run with the equation. And what happens is that very quickly it attains the maximum level and starts propagating everywhere. So it starts invading the entire axon. These equations are called reaction diffusion equation in chemistry. There are Fisher KPP equation in mathematical biology. It's really the hardcore, the fundamental equation of almost all mathematical biology, one of the first and most important one derived by Fisher in 1937. What you have is a systematic invasion. In mathematics, these are called parabolic, nonlinear parabolic differential partial differential equation, and a lot of properties of these are known all the way back from Fisher, but they're still very much studied because they're not only important, they're also very complicated and have a lot of interesting behavior that are directly relevant to a lot of invasion processes. In particular, you can directly get the velocity of this invading front, so they call invading front through the axons. So we understand everything about one dimension, but of course the brain is a little bit more complicated than that. So chapter 3, I'm passionate about three-dimensional shape. Now you want to go, you have the model, and you understand its elementary behavior in a very simple situation, either completely homogeneous or just in one dimension. What you want to do is what would happen within the brain with that process. So you need a brain. Good thing, plenty of brain. So here is my colleague Alan Kuhn in Stanford, where we went to Stanford, and with Mehmet Turk, who is now at Stevens Institute of Technology. We put Alan in the MRI, and zoom, 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 zoom. You slice her, or slice brain, take slice image of the brain, and you get this nice black and white picture. And the second step out of that, out of the black and white pixel, is the segmentation process, changing that into what's called a mesh in computer graphics or finite element, so that you can actually do computation, transform that locally in little triangles or tetrahedra, if you want. So you have the full three-dimensional shape out of that. This is not, this by itself is not obvious step, and it's not done automatically yet. There's a lot of interesting mathematical and technical issues related to that. But eventually what you get is this. So this is Alan's brain and a skull. So what you see in green is the cerebellum, right? This part is the white matter, and then as it evolves, you get the cortex, the cortical, the gray matter, and then the skull. So you have a full representation, a computer representation of a brain. You need a little bit more, because you also need to notice direction of the axon. But there is a technique in MRI medical imaging called diffusion tensor imaging that allows you also to get this direction very precisely. And what you get is this essentially vector field that describes the principal orientation at each point in the brain of an axon, of this axon of filament. And you can reconstitute that and have all the direction. So we've got this is actually Johan's brain. It's not Alan's, but you can. It's the same type of mesh. So okay, so you have a brain, you have equation. All you need in order to finalize, to start simulating the process, is initial data. Or are you going to seed? And the seeding depends on the disease and on the type of protein. So you go back in the literature and you find that depending on the type of protein, you see the first presence of this aggregate at different places in the brain. So depending whether you have amyloid beta, or tau, or alpha-synuclein, or TDP43, you essentially have initial data here in the brain that you see on these slides. And so this is what we did. And the only thing we're going to do now is run the same model on these different initial conditions, on these different seeds. Here is a run of for the tau propagation in Alzheimer's disease. So on the left side you have the propagation over time of the brain, and on the right side you have propagation at mid-time of the slides to see what's inside. It took long enough to do this movie, 2 weeks of simulation, so showing it again, making the best out of it. It's pretty cool. So you do that on all the different ones, and you can go back now to the Braque staging and see how that compares. And here is the evolution that we found for the different type of disease, the different type of protein. It's the same model with essentially the same parameter, but with different seeding. And what essentially you get is that you recover most, at least qualitatively, and in some cases quantitatively, most of the staging process of the brain, directly from the simulation of these equations. I told you we'd go back to ALS. You see that in ALS, The back of the brain, as I told you, is not directly involved in the late stage of the disease. The occipital is not infected. Whereas in T's progression, you see that you always have that. There is no way to stop that, really. There is no process that would stop that from happening. And so that's interesting, because it's always good to have a model that works in certain cases. You feel you understand something, but you also learn something when the model fails. That means there may be something, a mechanism in ALS that may be different than this other neurodegenerative disease in terms of our damage and propagation of the disease. And that's one of the aspects that we study now. You also see that there are some parts of the brain that are last affected, like if you see here the back of the occipital lobe, the top here, and this is well known. And the standard explanation that you find in the medical literature is that the type of tissue that you have there is less prone to being invaded, is more resistant, less vulnerable to the disease. What this simulation shows is that these areas are not affected because they are the last one to be affected. In that propagation process, they are the furthest away from the invasion of the disease because of the very complicated form. Now you can go back and look at the abnormality that we talk about, and this is essentially the Wheeljacks curve that we obtain from the evolution of the disease for different types of protein. And again, what you find is very interesting is amyloid beta always start before tau protein, exactly like what's found in Alzheimer's disease. And the reason might be that it is the place where the disease starts that's less connected for the tau protein than the amyloid beta. That's why you see amyloid beta before. And a lot of emphasis in the 90s was on the amyloid beta hypothesis. It's the first one we see, so it was thought to be the mechanism, and all the drug and treatment antibodies were designed in order to reduce the plaque, and that may or may not work. But now people are thinking about that and thinking maybe the tau protein also is important in that process, because some of this treatment remove the plaque, but doesn't change the evolution of the disease in terms of cognitive function. So now, that was for the biomarker abnormality. We want to go back to the physical world. What does it do to the brain? Here's a patient with Enzyme at year 0. And what we do is we segment it, so we get T, so just on the coronal slide, and then we let it evolve in time. So we go from here to here, and then we simulate that. So we go to that, and we let it shrink by a mechanical model. I'm not going to go into the detail. Essentially removing part of the material in the 3D mesh and recomputing mechanical equilibrium. That's year 1, that's year 2, and you can start the shrinking process. And that's year 3. Right? So that's again, we go from. So we establish the mesh early on, and we run on the top row, and the prediction is the middle row compared to the real disease. It's a very good match, fortunately for the patient. Here in a movie, it's much easier to see. So that's the evolution. And what you see again is the enlargement of the ventricle, the opening of the subside, the thinning of the cortex. What you see in red is really the stresses that we compute, the so-called von Mises stress in engineering. So we got this picture that has all the building blocks. We understand some aspect of it. And of course, at first you can be very happy. But then the next question is, why does it work? There are two things you can do at that time. You can either specialize your model and put more and more mechanisms that are known to be important, maybe the vasculature, the metabolism, various aspects of genetics of the brain that we are considering. But what you can also do is generalize and say, well, wait a second, why are all these models that describe very different type of disease actually work and reproduce this very systematic staging process, this invasion process? What element is crucial for that? And the idea that we had when we started, that what's very important in the brain is the brain architecture, both the geometry and the topology, the way it's connected with each part. And so you can try to probe that a little bit more by further simplifying the model. Say, if that's important, can we run a model that just extracts this information for which we can do more mathematics and maybe get a better understanding? So this is chapter 4 for us. the struggle of whether we connect more by a great philosopher over time. So it's about connection. So we go back to the brain and say, okay, what you can do is say this is quite complicated. It takes a long time to run this equation on this match and all that. So we can simplify. We can define region of interest. We can take a brain atlas and say, okay, here is a region, the temporal pole, and so on. And we can define multiple regions, and then look at the number of connection axons between one region and the next one. So we can start counting how these different places are connected. And you can do that to the entire brain. For instance, here is an 83 node brain. And once you have that, you can start labeling these nodes, 1, 2, 3, 4, and so on, 5, 6, and look at how the nodes are connected. And from a graph like that, a three-dimensional graph, you can create a very simple mathematical object that represents the connection, that extracts the connection. So let's look at an example with 6 nodes, for instance, 1, 2, 3, 4, 5, 6. It doesn't have to be connected like that. But what you want to do is to represent completely that graph by an array of numbers, a matrix. Here is the matrix, called the adjacency matrix. And what you do is very simple. If 1 is connected to 2, you place a 1 in line 2, column 2, and column 1, line 2. Okay, we can all do that. So 1 and 1 there. Okay. So for instance, 6 is only connected to 4. You see 6 is only connected to 4. So line 6, column 4, column 6, line 6, column 4, you have a 1. And 0 everywhere else. You have the total information about the graph in that matrix. Matrix of 0 and 1. Okay? You can do that for the brain, the 83 brain, or you can do that for T's brain, which has 1,000 nodes. So T's one is an average based on 419 healthy brain from the Connectome Human Brain Project, Connectome data. And I put it in color because colors are prettier, and it also contains a little bit more of information. Blue is 0 and red is 1 as before. But I weigh the connection by the number of axons between region I and J, and I divide them by the length. So the connection is, the weight is lower for large lengths because it's further along. So it's a way to measure transport process. And what you see is stunning. I think it's a beautiful picture. Whenever I see this matrix, whenever I've been given linear algebra or matrix course, where you see the matrix and you can see right away that it has biological meaning, or meaning that directly reflects us. What do you see on this picture? You see that it's mostly 2 big blocks. And these two big blocks are the right hemisphere and the left hemisphere. And you see that they are poorly connected. These blue things tell you that the right is not connected to the left, and the left is not connected to the right, and the only place where it's connected is this corpus callosum that makes this connection between the two hemispheres. So right away, when you see this matrix, you see the brain structure. You can actually see much more structure. It has also all sorts of nice property in terms of connection. There's this small world brain network, like small world friends, friendship network, and so on. It essentially means that you have regions that are very closely connected to each other when they're close together, with a few long-range connections that establish it. And that dramatically lower the distance that you have to go from one node to the other one. Okay, on average, this is the path length distance, the average path length distance is between 2 and 3. That means on average, if you take 2 random nodes, you only need between 2 and 3 steps in order to connect them by node. It's very close. And that you see with this kind of butterfly structure here. So that's just for how the brain is connected. You want to go a little bit further, and what you want to do is transport on a graph, because we're interested in the way these proteins are transported in the brain. There is a very nice and simple way to do transport on a graph. Is imagine that you heat one part of the graph, and you look at the distribution of heat. This distribution is actually given by another matrix that you can compute with from this matrix. It's called the graph Laplacian, which is the discrete version of the heat operator, of the diffusion operator. And it's very easy to build. Wherever you have a 1, you put a -1. We can all do that, right? And on the diagonal, we count the number of 1 in the matrix. There are 2 1s on the first line, I put a 2 on the diagonal. 3 1s on the second line, I put a 3 there, you see? Okay, so I think we can all, with pen and papers, we could all do. So this matrix is fundamental for all network analysis. It contains a lot of information about connectedness, but also about transport. And now we have all the pieces that we need in order to create a model for the evolution of this protein on a network. Instead of using the continuum model where the proteins are defined at all points, we use a discrete model where we only define the protein in this region of interest, so a finite number of them. In the left side for the continuum model, we have partial differential equation, and on the right side, it's become discrete ordinary differential equation, where the Laplacian, the transport operator, is replaced by the graph Laplacian in this case. And the difference is partial differential equation is that these on the left take a lot of know-how and a big computer running for 2 weeks, and the one on the right you can run on your Apple Watch. About that level of complexity. Well, maybe not for the 1,000-word model. Maybe the new version of the Apple Watch. Okay, so what does it look like when you evolve? So here we look at tau protein and we see them at the entorhinal cortex and we let them evolve just like before for the continuous model. So you see the right hemisphere and the left, right on the left and the left on the right. And you have the evolution of the disease going through different stages again. So doing so, you've really extracted the simplest possible. There's very little knowledge that you have from the initial brain, just how things are connected essentially and the distance. So here is another simulation where I just start at the temporal pole here, and that's to simulate frontotemporal dementia, which is happen first on the left hemisphere and then propagate to the right hemisphere. And I also, I'm not going to talk about, but I also overlay a model for the physical shrinking of the brain, so that you can compare the way this region of interest move to MRI data. So the main point here is that now we have clinical data on the top, we have a continuum model, and we can match that to the discrete model. We have different resolution for which we can learn. The advantage of the discrete model now is much simpler to study theoretically, and you can grab some of the interesting properties. So if you compare the two, you can look at the staging, for instance, for, again, the tau. In the two gray and black, you see the network and the continuum in terms of the evolution of the biomarker. And you see with this level of discretization, it is actually very good. And you have the different evolution for the different lobes, the temporal lobe, the frontal lobe, the parietal and the occipital. And you can compare that now to the best so-called Wheeljacks curve that you can find around, which essentially you recover all the known qualitative features that have been established and some of the quantitative ones. But you can go much further now. You can study mathematically this solution, and what you can show is that the primary infection that takes place in all these neurodegenerative disease is a topological property of the connectome. It always happens at the connected node of the seat. And that's where you go from limbic to basal ganglia to temporal lobe infection. The secondary infection, you can define a secondary infection that's a balance between kinetics and transport. So at first, what really matters for the invasion process is how the brain is connected. And then it depends more on balance between distance and between kinetic reaction, what actually a reaction takes place after that. And that's why you can show it, because systematically from parietal to frontal to occipital. And so you can make sense, and in a rigorous sense, of this evolution process. So you feel like you've gained a little bit of understanding. So let me finish with what Voltaire called the first law of nature. And the first law of nature, according to Voltaire, is to forgive somebody else's stupidity or folly. So in any given discussion, you have to forgive somebody else's folly. So that's why I ask you of me when I present you such simple ideas that you have to believe in when it comes to that. So what are our conclusions for this process? We understand a little bit better the staging, and I tried to demonstrate to you that the staging process that's so what doctors call homogeneous, that means systematically taking place in the same way for different patients in the same disease. The reason why it's homogeneous is because of the geometric and topological nature of the brain and the way initially the brain is seeded by this protein. We understand better atrophy as a process of removal matter, and you can now test different types of damage mechanisms that will lead to different patterns of atrophy. And finally, we give some sense to this Wheeljacks curve. Yes, by the way, Jacks, according to a model, was correct in his thinking of the evolution. But it's no surprise, the way, the minute you write a model like that, you know that you expect this curve to be like that. So it's a little bit coded directly in the model. There is no surprise there, I would say, when we know a little bit about the behavior of this equation. So we have a better understanding of that. We have a computational platform that shows you the evolution of that, where you can systematically look at the evolution of different models, more complicated models in terms of the kinetics, and you can start testing different types of ideas about interaction between these proteins. For instance, how does amyloid beta and protein and tau protein interact in the disease, and test different possible mechanisms for that. And so to finish, I want to bring us back to the 15th century. This is one of my favorite paintings from Hieronymus Bosch. It's called The Stone of Folly. And here is a practice that was done at the time where somebody who had dementia problem would go through an operation where somebody would actually try to remove the stone of folly that was in the brain. And the stone, so here is the patient here suffering, you see, and it has removed part of the stone of folly right here on the table. So when you look at that, you have to decide who you are, who you want to be. You want to be the patient that's ready to have any type of operation, or ready for anything, completely desperate. You want to be the woman there is represent the public at large who believes in everything, because the idea at the time is that by putting a book on your head, you would acquire the knowledge from it. You want to be the philosopher, the person, the religious person thinking about ethics, but also drinking a lot of wine at the same time and telling people that it's okay to go through that. Or you want to be the scientist or the medic here who goes also drinking, does his operation, who has a funnel on his head to indicate that himself might not be well in his head. That's the indication. And that tells us that maybe the idea of being able to understand our own brain is the ultimate folly. Thank you.
Thank you for the fantastic talk. We'll have a couple of minutes for questions as well.
I have two questions, sir. Amyloid plaques versus tau protein, which of them is more linked with mathematical calculation?
So, I'm not sure I understand the question. So what the model shows that we understand why, if you start the two processes at the same time, and you say both are going to start at a different place, then our model shows that you should see first the amyloid beta rising faster than the tau protein. Right. So that's what it shows. Mm-hmm. Right.
Second, you mentioned that it is a prion-like mechanism.
Yeah, it's an hypothesis. Yes.
Is a toxic protein, is it infectious or non-infectious, and how patient gets in the first place?
Yeah, so unlike prion disease, neurodegenerative disease are not infectious. Mostly, I don't think there any knowledge of that. You can infect in animal model, you can do that, but they're not infectious. So what happened is the prion idea is a little bit misleading because for prion disease the protein is really misfolded. But what happened, for instance, though protein is a little bit different, is that you can have a hyperphosphorylation of some site on the protein itself, and that can create the ability for some other toe to bind with it. And that is this first initial binding that can create further aggregate at the same time. So the nature of the misfolding, or the isoform of the toe protein that you find is quite different than the misfolding of protein in prion disease. And that's why it might not follow the same pathology infection.
Your model of the connection and the movement of tau via the neuronal connections assumes a healthy state brain. Have you overlaid that on an atrophying brain? Because presumably a lot of those connections are degrading throughout the disease.
Yes, that's a great question. It's one thing that, so the idea is that, well, wait a second, as the brain degrades, the transport is going to be affected because it's not going to take place in the same way. I think that's what it is. Right? So yes, we tested that explicitly by having an evolution of having a damage for the weight themselves and the change in space. It turns out, which I find fascinating, that it has no effect whatsoever. Even if you push the parameter way ahead, it has no effect. Because the only thing that matters is what ahead of the front. And we understand it mathematically what's the case in the type of front propagation. But the way to think about it is that what matters is initially you see that little bit you connected node, your neighbors. Even if you sever this connection, as soon as your neighbors are seeded, they're going to start, the infection is going to start growing there. So you don't need the connection at that point. And the connection, the way that the damage really only takes place in the final phase. So even though in principle there is, when you take that into account, you show that it has no effect. However, it has an effect on the cognitive process because these weight change. So the way the brain synchronizes or the way the brain organizes changes in the process. And that's more exciting and interesting to do. Yes?
I was wondering, does this throw any light on any possible clinical treatments? I mean, that's a long way.
Yeah. That's a
to
decent question.
Yeah.
I think what it gives us, so the short answer is no, I'm not going to pretend I have any. But what you can identify in this process are always what is the interesting therapeutic target, what are the mechanisms that matters or not in the process. Like somebody suggested me once, well, if the connectome is responsible for the evolution in the diseased brain, why don't you just cut this connection? Well, actually, the mathematics show that no, if you do that, it doesn't change. Well, it'd be bad for the brain in the first place, but it's not going to change anything in the infection process. The typical way, what you can do is two things. You can try to increase clearance, that's the idea of antibodies, or reduce production of these, right? Try to control these. It gets much more interesting when you look at this extended model, where you look at each oligomer, so each of these aggregates of protein of different size has a different species. And then you can start comparing how these evolve in order to better target which one you want to address with antibodies. One of the problems with antibodies is that as they flush into the brain, they can get rid of certain type of aggregate that might not be bad for the brain at all. They can just suck up these that are not. And so you can start testing them. And one of the ideas, for instance, something that has been shown here in Cambridge, is that small oligomer of amyloid beta are actually much more toxic than large one. When the plaque is established, it's basically there, it doesn't do that much. And most people in their old age will all have amyloidosis, amyloid beta plaque, and that might be perfectly fine. But now you can start targeting at place where the biology and the experiment cannot look. It gives you a microscope to look at this case, because the evolution of this protein cannot be understood in vivo by any clinical means. But you can look at the evolution through this equation, this model, and make some prediction about the evolution. And it's combining the two that it gets interesting. It gives you another tool for identifying mechanism. And my belief is that, yes, it's nice to be able to cure a disease even though you don't understand it, But if you can cure it for 30 years, maybe it's time to try to really understand the details of it and identifying the mechanism.
So I was wondering, in the discretization, the graphs seem to be undirected.
Yeah.
From the continuum case, I would assume that wouldn't be the case because of that B. It seemed to be all over the place, and the discretization seemed to lose some features.
So it's very good. So the continuum case, the operator doesn't know the end tail of the axon, whether it's up or down.
Oh.
So it's also undirected.
I see.
But the brain is directed. There's very clear directionality in the way the connection takes place. Whether that reflects directly on the transport process is not that clear, but they are evident that it might. The big problem is that we have very little or no data on directionality in brain connectome. In human brain connectome, there are such data in mice for you can apply it. So what it changed is that the graph Laplacian that I showed was a symmetric matrix, and it becomes a non-symmetric matrix, and you can apply these ideas. It leads to a lot of interesting mathematical problems that people have not looked, because almost all the literature is about symmetric graph Laplacian. And so the non-symmetric case is both mathematically interesting, but also potentially very important. And to go back to the ALS case, I think directionality might be key to understand the patterns of invasion in ALS. So it's a very good point.
Thanks for that. Can I just also ask, your seeding parameters, are they chosen based on in vitro studies that have looked at the seeding of those proteins, or do you just modify the seeding, sort of rate kinetics, for instance, of the...
So that's another good question. So the experiments in kinetics that are done in the lab in a homogeneous environment, and that shows very quick evolution over 7 days or so. You can do experiment where you create these alpha-synuclein aggregates, or these tau aggregates, or these amyloid beta. So it's in that order. And then you think, wait a minute, it happens so quickly in these in vitro experiments. Why is it so slow in vivo? How do we explain it? What are the processes that slow down? Was one of my first questions, and I don't have a good answer for that, is that why is this disease so slow? Why does it take 30 years of evolution? I mean, most disease that we know are much shorter in time, right? I mean, in the last stage, of course, it could be dramatic. It could be 6 months in the case of ALS when you put first symptom into death. But there is a prodromal phase. Before that, that's very extended. I do not know really the right time scale. What we understand, for instance, the prion, it's already known that there is a scaling in these kinetic parameters between in vitro and in vivo. That the way the cell environment changed the kinetic by large factors. And it's believed that in neurodegenerative case, it is also a scaling by order of magnitude of these kinetic parameters in order to have the right time scale. But what you cannot do is take the kinetic parameters that come from in vitro experiments and directly use them in vivo. Otherwise, you have evolution, because diffusion is rather fast. Diffusion between 2 points in the brain is a rather fast process. So you have to find a way to slow down. And that's why we thought that amplification of oligomer population might be key. That not only you have to transport seed, but when you transport seed, you start to have to make them bigger, because it's very hard to transport big particles. And so keeping track of the size of this population at different places of the brain may be key in order to have these slowing down, understanding time scales. But as in all I've seen, they're more or less introduced artificially this time scale in order to scale for the disease.
Regarding that point,
Yeah.
the model doesn't reproduce the right time scales in the evolution of the disease, just the spatial pattern?
So the model has a few parameters.
I see.
And there is one parameter for the diffusion operator that we set so that it looks like it's 30, t equals 30, but that's arbitrary scale. I don't know to scale them properly. I mean, we have a diffusion, we know about property of diffusion in the brain, right? But the direct property of diffusion in the brain do not scale directly to how infected tau protein can go from one place to the next one, because there is a lot of process within the axon that have to take place in order for that to happen. and also scale with the size. And the scaling with the size, the scale, diffusion scaling, mass scaling of diffusion is also very interesting. And that's more a statistical physics problem, but it's also fully understood in terms of propagation of independence.
So the velocity basically will change over time of the process, or am I mistaken?
No, so we set, I don't know what you call like velocity.
I don't know the probably.
No, when we set it, we don't cheat anymore, but we say this is the evolution of the disease, take that to take to the maximum value.
I see. Okay.
And in simplest form, actually, you can further reduce. I show you the model at like 4 or 5 parameters, but actually you don't do only 2 parameters once you do all the proper mathematical tricks of redimensionalizing and things like that. So there is one parameter related to diffusion and one for the amplification. That's it.
Do you see a potential for applying this model to a combined dementia where a patient has Alzheimer's and another dementia?
Yeah.
What would happen?
Yeah, so that's very interesting. So now we have this tool, and one of the questions we had, first question was, how do different protein species interact? I think that by itself is interesting, see the different places, but we know, for instance, that amyloid beta has an enhancing effect on tau protein, both in terms of changing the environment and create hyperphosphorylation, but also in they both combine and create more damage in the cells when both are present. So that by itself is interesting. But the point that you raise is even more interesting, is that most of the neurodegenerative in the last stage, they all show the same type of pathology. You can converge towards the same type of disease in a way. And by the late stage, it's hard to define which one is really which in terms of presentation of the symptoms. So there is a lot of comorbidity, for instance, between vascular dementia, that I didn't talk about, which is more related to the health of the vasculature within the brain, and maybe not directly related to protein, and protein-related, like Alzheimer's dementia. And it's known that these are connected, but we don't know exactly how. So in terms of linking Ts, what we're now doing is coupling Ts with clearance map produced by vasculature model. So it's another type of physics, it's another type of process, but you can look at the way the blood in the brain is being perfused, and all that change due to microthrombic event, to stroke and things like that. For instance, 40% of strokes eventually lead to dementia, or Alzheimer type. So there is all this correlation. And we're looking at this coupled model to have a better, more realistic understanding of this type of interesting interaction between dementia.
Obviously, this is one hypothesis. Have you tried modeling any of the other hypotheses for the causative agent of Alzheimer's?
So the other one are amyloid. So the one that I know, maybe you know more than me.
The other one I was thinking was inflammation.
Yeah. So you can look at the local change in the environment related to metabolism and related to inflammation. The other one is vasculature, related to as the causal. So people think that all the problems related to dementia are actually created by change in vasculature, and that the protein that you see is like the canary in the mine, the one that dies, but that's not the cause of the mine. So we're talking now with groups, a couple of groups in London and Toulouse, who have this model of evolution of vascular dementia, because there is a lot specialization in terms of computational fluid dynamics that you need to do in order to do it properly. By itself is an interesting modeling field, in order to be able to both compare them and combine them as a certain way. But the short answer is no, I haven't looked at it.
Aggregates are extremely diverse. Like, for example, we know that oligomers might be more toxic than other species. But there is a great heterogeneity in the structure and size of the species. So we even don't know which population might be more crucial to the whole pathogenic process. So how do your model cover this issue?
Yeah, so the model, I didn't show you the detail, is coupled to a damage. And the damage itself could be a function of the different type of oligomer. So I think you have a couple of questions. There may be, for a given size or for a given number of protein, you might have different oligomer already. But that gets a little bit too complicated. Mostly people agree that these one are mostly linear oligomer that you can do. And that's a reasonable approximation in view of the experimental evidence. So yes, you can relate the damage to the size of the oligomer explicitly in the model, but we haven't done that yet. We're setting up the tools in order to be able to do that. Yes, so as I said, the small oligomer of amyloid beta are known to be much more toxic than the large one, for instance. But you can put that explicitly.
Okay, thank you so much. And can we give one last round of applause for the fantastic